So welcome to the SPAAM seminar. And today we're going to have our first speaker is going to be Grega, and he's going to talk us about random walks in spin systems.
Okay. Okay, everyone, thank you for inviting me. So I'll present an example of a system that would start with mechanics, and then I'll shortly give a brief overview of some techniques that we can use. So we can use random walks, show how, and then show a technique from random walks. So one of the things we're interested in statistical mechanics are magnets, and one of the simplest models for a magnet is that we have a lattice in ZD. So in this case, you can set D equal to 2, but it could be in any dimension. And so this lattice is supposed to represent crystal material. And then at every vertex of a lattice, to every vertex, we assign a spin to it. So either spin up, so arrow up, or spin down, which we then represent with numbers plus or minus 1. So plus 1 for spin up, minus 1 for spin down. And then a vector phi encodes all of these spins and represent a possible configuration of the system. And then what we want to do is we want to assign energy to each one of these configurations. And the way we do this is we look at all of the neighboring sites. And so, for example, if you look at this site has 4 neighbors, and then we look at whether the spin at 2 neighboring sites are aligned or not, right? So if they are aligned, this product is 1. If they're not aligned, it's minus 1. And then we sum over all sides. And so, as usual, the system will prefer to occupy a lower energy state. And so in this case, because we have this minus here, this will be the smallest when all of the spins or more spins are aligned. So we are encouraging alignment of spins, which is then called a ferromagnet. If we replace this with a plus, for example, we will be encouraging misaligned spins, which would be then a paramagnet. So if a material that usually doesn't have magnetic properties. And then with these definitions, what we are usually interested in is the so-called two-point correlation function, or the Green's function, which basically looks at the correlation of spins at, let's say, site 0 and some other side, which would then like to take some distant side. Okay, so with the correlation, so of course this has to be probability. So we're looking at the expected value of this product, right? So we sum over all the possible configurations. We look at the value of spins at these 2 sides, and we weigh this value with the probability of that particular configuration, which is, for physical reasons, is proportional to the exponential of minus beta times the Hamiltonian. Beta here is usually taken 1 over the temperature, so inverse temperature. Okay, so and then we have to normalize this factor just to make this probabilistic. Okay, so basically the probability of a configuration is proportional to this factor, and then we calculate what is the expected value of alignment of spins at some site 0 and some other site x. And then we do this in infinite volume limit, meaning we're increasing the lattice to infinity. And as mentioned earlier, so what we're actually interested in is how this function behaves as we push x to infinity. Instead, in whether there is any correlation between a spin at some site 0 and some faraway site. And actually, it turns out that this is an Ising model. There is this correlation depends on this inverse temperature beta. Right, so if there is such a critical value of beta, such that if beta is less than beta c, so we mean high temperature, this 2-point function decays exponentially, meaning there is no real correlation between spins at 2 distant sites, and we get some sort of disordered system. So imagine the white spots are +1 spins and the black ones are -1. Then if beta is above the critical value, so meaning lower temperature, this correlation function does not decay, meaning there is correlation even on the large scales, and we call this long range order, and we might see something like that, for example. So most spins are aligned, And other critical value, you get some sort of large clusters. At that value, turns out that this correlation function, the Green's function, is became polynomial. And so actually, this is usually the hardest decay to analyze, so other criticality. And the way we do this usually is we use a trick. Basically, it turns out, I won't exactly explain how, but it turns out that we can rewrite these interactions between neighboring sites using random walks. And then instead of studying the Green's function of this form, we get some other Green's function that looks more complicated. I guess it is more complicated. So this is expectation with respect to a random walk that starts at 0 and forced to end at subset x. This function z then looks like something involving continuous time random walks, Brownian bridges that interact with themselves. Those interactions represent particle interactions. And this one x just means that we also add our random walk between those Brownian bridges. And we integrate over all the possible random walks. So it does look more complicated, but then the reason this is useful is because once we represent this using random walks, we can use some techniques that are available from analysis of random walks to try and analyze asymptotics of this function. So I won't show you those techniques on this example because this will be too much involved. So I will show you a simpler example, a simpler example of the Green's function, and I will show you how we will analyze that kind of Green's function. Okay. So this will be a Green's function for just a simple random walk. So imagine you have a random walk starting at 0 and ending at site x. So for this technique to work properly, usually you need a dimension to be at least 5. And imagine you want to somehow quantify the number of walks between 0 and x. What we would do is we would sum over all the random walks from 0 to x. So this is the sum. But of course, there are infinitely many random walks between any 2 points. So this sum diverges. So we add this sort of convergence parameter here. So beta raised to the power of the length of the walk, where beta is some parameter between 0 and 1. Now, if we stop here, we'll get something that is called the Green's function for a simple random walk. This is a random walk where we do not care how the walk actually looks like. But usually, because we're interested in in the interactions, we want to study a random walk that we call it weakly self-avoiding. So we want to study random walks that tend to avoid themselves, tend to not self-intersect. So we want to somehow penalize these self-intersections. And we achieve this using these sort of factors. So we can evaluate in this form usually. So we have this function u that depends on the position of our walk at 2 different times, s and t. And if the walk intersects itself at those 2 times, then this u has a value lambda, otherwise 0. So at the intersection, we get a factor of e to the power of minus lambda, which is less than 1. And we take this product over all the possible time pair combinations, right? So at the end, for every single self-intersection of the walk, we will get a weight of e to the power of minus lambda here. In this case, we have one self-intersection, so we'll add e to the power of minus lambda here. If we set lambda to 0, we just get back the original random walk because this is always 1. And in this representation, you can think of, if we sort of set lambda to infinity, then this would be 0 as soon as we have one interaction, self-intersection, which would mean we are strictly prohibiting self-intersection. And then this function would only count strictly self-avoiding walks. Otherwise, it counts all of the walks, but it gives lower weight to walks that have a lot of self-intersections. And we can already see asimilarity. So even though this, maybe you wouldn't expect this to have any sort of resemblance to the Green's function for the easy model mentioned earlier, we can already see that even in this case, we get some sort of critical behavior, where there's a critical value of this parameter beta, where this Green's function changes asymptotics. So as we push x to infinity, so we are looking at random walks between 2 very different, going from one side to a very distant side. below the criticality, we get exponential decay. Above the criticality, this function diverges, and under criticality, we get a polynomial decay. And again, this decay is the hardest one to obtain, usually. And so I will now show a technique called gas expansion, which I've been studying, which is quite useful in these settings, which usually allows us to get these kind of criticalities. And so it is a bit technical, but hopefully I can at least give you the main intuition about the main steps. So in this particular case, we sort of exploit a bit the exact form of these weights. So what we do is, so these are the weights we have earlier, the weights function. We sort of add and subtract 1. And now, so this UST is just shorthand for U of gamma S gamma T. And now take, for example, the length of the walk that has length 2. So it has, okay, it has 3 times because, you know, it also starts at time 0. If you write out this this product, and then imagine if you expand these square brackets, right? Every term you end up with will have a few of these ones and a few of these factors. So for example, if you multiply ones together, you get this one, then you can multiply 1 and this one to get this term, and then 1 and this 2 to get this term, and so on. And now what we can do is we can represent these factors, these terms, using something called order graphs. So these are still graphs, but these are not graphs in the usual sense, because so our graph has as many vertices as our work has steps, and we have to order them linearly. And then in this case, because we have this factor u with 1, 2, we present this with an edge that goes from 1 to 2. So this sort of means that we are sort of testing whether our walk intersects us at these 2 time moments. So this term here will be represented by a graph that has 2 edges, and for example, this one has no terms of this form, so this is just an empty graph. So this is an illustration how you can represent this weight using graphs. Now, of course, if you sum over all the possible graphs, you get back this weight. Right, so then you can write this weight as sum over all of these other graphs, and we're summing all of these weights. So we plug this back into the original Green's function. Now we're studying this object, which we'll see why this is promising, but there's a big this sum now has 2 main issues. So first of all, the sum of all the graphs is huge. It blows even more than it's exponentially, but the exponent itself is increasing. So this graph is huge, and also these terms here can be both positive. Are both positive and negative, and it turns out that this sum is not absolutely convergent. So if you want to bound it with absolute values, you can't just take the absolute values inside and hope to get something out of it. So we need to simplify this object. So first what we do is we want to replace the sum of all graphs with sum of the connected graphs. This is already a smaller sum. Now when I say connected, again, this is not the usual definition of connectedness, because these are other graphs. So what I mean by that is the first and last vertex have to belong to an edge. So this is true in both cases. But then for every vertex in between, there has to be an edge stretching above it, which is true in this case. So 1 has an edge above it, 2 has an edge above it. But in this case, this 1 does not have an edge above it. So this one is not connected. Now you might ask, why can we simply replace this sum with some of the connected graphs? Well, it turns out that these 2 objects are related with something usually called the Dyson equation. It's a form of convolution equation, where this S is something called the Green's function. So this S has the same form as G, just without these weights. And it's sort of easy to get bounds, it's asymptotics on this function S. And it's not easy, but it is doable to get asymptotics on this object pi. And then for this equation, we can then get asymptotics on G. So even though in some respects we have massively made our problem massively more complicated, we at least now have to deal with objects that are easier to analyze in the end. So this is what we gain. Now, so how do we bound this file? Well, it turns out that the sum over all connected graphs is not significantly smaller than the sum over all the graphs, because most graphs are actually connected. So we still need to somehow simplify this sum. And the main idea here is that instead of summing over all connected graphs at once, sort of partition our sum into sum over minimally connected graphs, which are called in this case laces. And then we sum over all possible combination of additional edges that we can plug into our minimally connected graph to get a connected graph. Yeah.
So maybe it's statistical, but what do you mean by minimally connected graph?
So it means that if you remove any of the edges in a minimally connected graph, you get a graph that's not connected.
Oh, okay.
Yeah. So you can think an analog of this is if you're dealing with regular graphs with normal, like regular notion of connectedness. Think of minimally connected graphs in those settings are trees. And then, for example, you have a Kruska's algorithm that takes a connected graphs and gives you a tree. And so in that case, you would sum, instead of summing over all connected graphs, you would first sum over trees and then sum over all the possible combination of edges you can add to a tree to get a connected graph. And then at the end, you should get back all of the connected graphs. And similar to Kruska's algorithm, for this to work, you do need to have an algorithm that takes a connected graph and assigns to it a unique minimally connected graph, which you actually do have in this case. Otherwise, it wouldn't really be well defined. Okay, and so this is just one line, but this is actually the main bit. This is called the less expansion. So this idea that instead of summing over something very big, you can sort of partition into two smaller sums. And the reason this works well is because this sum is sort of small enough that you can sort of push you can bound this sum in absolute value, actually using triangle inequality, and then you can neglect a few things and can get rid of this sum. And just a technical note, in this case, you do need that this has to be non-negative, because in that case, this factor is less than 1. So this only works for self-avoiding walks. It wouldn't work if your interactions were attractive. And then once you get rid of this sum, the sum over laces is something, sum over trees, for example, is actually much smaller than sum over connected graphs and has some nice combinatorial properties. And then you can do some sort of resummation, exploit these combinatorial properties of these minimally connected graphs. And you can actually, at the end, derive nice bounds on pi. So I won't show you the bounds because they wouldn't really be illustrative. But yeah, this is the main idea. So splitting the sum into two smaller sums. Now this was done, in this case, we did this for the existing function for the regular self-avoiding walk. In other cases, what changes to other more complicated Green's functions is that the algorithm that assigns okay, first of all, it's harder to sort of see this graph representation of your system. And then once you have that, you need a different algorithm that will assign a lace to your Okay, so why is this technique useful? Because you might say that you just use more direct techniques, but actually this technique allows us to get asymptotics for a wider range of parameters. So for example, asymptotics of the Green's function at the critical value of beta. Usually you can't get that using other techniques. In some cases, it allows you to remove some of the assumptions. So this goes back to the Ising model I mentioned earlier, which when this was first done, they didn't have to assume as many things as you would otherwise. And then maybe potential future applications would be, we could try and study more than just two-body interactions. So imagine this U depends on 3 or more parameters. And then this could also translate into studying modern statistical mechanics that have more complicated interactions built into them. We could try and study attractive interactions, and we could just, this is actually what we are trying to do now, is try to apply to some statistical mechanics models where it hasn't been applied yet. But usually the challenge is to But the first challenge is to just write your system in a form that will allow you to apply the less expansion. And then the other challenge is to figure out all the technical details that can be done. And okay, just for the end, I guess this actually comes at the beginning, but in this case, I thought we'd better put it at the end. Some literature review. So this technique, the less expansion, was introduced in 1985 to study random walks, and then actually much later, mathematicians started realizing that it can be used in other models. Yeah.
No, sorry.
So, for example, in 2003, it was used to study percolation. Roughly, percolation is a study of if you have some big connected components in 2 dimensions, how big those components are and if they are infinite. So in 2007, it was used on the Ising model, the model I mentioned at the beginning. And for example, in 2016, it was used to derive a local central limit theorem for self-avoiding walks. So it's still useful also if you just use it for self-avoiding walks. And yeah, that's all from myself. Thank you.